So the rate at which an object cools or warms is inversely proportional to the temperature difference between the object and its environment. So basically, the larger the temperature difference, the less time it takes to cool, so the quicker it cools. So if you have a larger temperature difference, it cools quicker. Same thing with warming. If you want to heat something up, the larger the temperature difference between the object and what you're heating, or the environment it's heating up in, is going to do it quicker. Okay? There is an equation for this. I'm going to give it to you. You do not have to memorize it, and you're not going to have to solve it. You'll see why in a second. But it may be helpful in you remembering or having to explain this idea. Okay? So here it is. Okay? Just prepare yourself. dt over dt. So this is calculus speak for change in temperature over change in time. So the rate the temperature changes in a rate of time, so the amount of temperature change in the amount of time, equals negative, which is the inverse idea, K. And you might be saying, like, oh, that's Boltzmann's constant. We talked about that before. Nope, it's not. It's called the cooling constant. Yep. Yep.
Why isn't it a C?
Because C is something else. Of course, K is something else, but don't worry about that.
K is cool.
Yes, ma'am.
So is that a D or a 2?
This? Yeah, it's delta. Here, we can make it a little simpler. We can use the triangle delta that we've used. This symbol here is like an alternate delta, Greek letter delta, and it's used to show derivatives in calculus. Like I said, I'm not going to make you solve this. I'm not going to make you solve calculus and physics too. But it's times the temperature of the object minus the temperature of the environment. Frequently, it's called the ambient temperature, which means the temperature around you. So there's the equation. Change in change in temperature over change in time is equal to negative K, so negative cooling constant, times the temperature of the object minus the temperature of the environment. Yeah?
What is the cooling constant?
It's a measure of the material the object is in, so like if it's in air or in liquid or something like that, as well as the size of the object and what the object's made of. Nathan, do I need to move you so you're not constantly talking to Lucia? Or I can just switch to Lucia too.
Well, I mean, I'm wondering if I can't write the board.
Can you not? Do you need to be closer?
Yeah.
Alright, switch with Zane. You can switch with Zane. Zane's got glasses. He doesn't need to be
I'm
close.
so blind.
Well, switch with Aiden.
I need them changed every year.
Huh?
I need my glasses changed every year.
You want me to switch?
Can I actually trust you and Zane together?
Sure. Am I moving or not?
Do you mind moving, Aiden?
No, I don't mind.
Okay. We'll see if this actually works. All right. So there's your equation. Let's do another thing here. So here's a nice simple graph to show you what this looks like. So here's time. Here's temperature difference. And basically, the time it takes to cool increases as the temperature difference decreases. So as you get lower and lower and lower in your temperature difference, it takes longer and longer and longer to cool. Now, let me be clear on this. That doesn't mean that it's going to take less time. Let's say you want to get it to 0. Let's say you want to freeze water. Okay? And you've got water, so you need to get it to 0 Celsius. And you've got 10 Celsius water, 10 degrees Celsius water, and you've got 100 degrees Celsius water, boiling water. That doesn't mean that the boiling water is going to freeze before the cold water. It just means that the time to go from 10 to 0 and the time to go from 100 to 90, it'll cool from 100 to 90 quicker than it'll cool from 10 to 0. That's all it means. Okay? That's all it means. So it's just telling you like how long is it going to take to do something, so the temperature difference there, okay? That's what we're looking at. I'll show you another example here. So again, this idea of if you want to change the temperature by 10 degrees, then the larger the temperature difference, the faster you'll change by 10. Here's another good example here that I'll give you as well. Coffee, okay? So you've got your coffee. Two circumstances, okay? So one coffee is at room temperature, okay? So room temperature, let's just say, is 70 degrees Fahrenheit, okay? And you've got your cup of coffee, okay? Ooh, I'm even going to be, yeah, here we go. Okay, there's your cup of coffee. And your cup of coffee is boiling 212 degrees Fahrenheit, okay? And you want to cool it off so that you can drink it. So you want to get it to, let's say, 120 degrees Fahrenheit. That's the temperature you want to reach. Okay? You want to get to 120. So if you cool it to 120 from 212 in an environment of 70 degrees, it'll take a set amount of time. Okay? I don't know how long it'll take. I can calculate it, but I'm not going to. Okay? Then I have another option. Okay? So I just leave it on the counter, and I let it cool that way. But my 4-year-old, she gets an idea. She also drinks coffee, and she knows a lot about physics, more than me apparently. And she says, okay, instead of putting it on the counter, what if I put it in the freezer? Again, I still want to get to 120 degrees Fahrenheit. So I still want to get to the same temperature. So the temperature difference that I want to reach is the same. But the temperature difference between the environment and the object are not the same. So which one will reach 120 first? The one in the freezer, because the temperature difference is larger than it is otherwise. Okay? So that's the idea here of Newton's law of cooling. The larger the temperature difference, and again, like you guys intrinsically know this. If you want to cool something and you just blow on it, that won't cool as fast as if you put an ice cube in it. Or it won't cool as fast as if you put it in the freezer, in the refrigerator, or something like that. Or leave it outside, or something like that. So the larger the temperature difference, the faster something's going to cool. That's also heating as well. If you cook something in the oven at 400 degrees, that will cook faster than something at 350 degrees. Okay? It may not cook as well, but it will cook faster. Okay? If you want to get it to that temperature, it'll get to that temperature quicker. Okay? All right. Any questions about Newton's law of cooling? Sweet. Okay. Go ahead and go to the other worksheet that you have out. This point of view worksheet. Let me show you how this one works, and then I'm going to give you time to work on it. And then we'll see where we are. There's at least one of the videos. You picked up that video sheet. There's at least one of those I'd like to watch. If we got time here.